Okay, dear students, let us start from where we left in the class a month back, and let us start with Hahn Banach theorem. Now, Hahn Banach theorem is one of the most important three theorems in functional analysis, along with the closed graph or open mapping theorem and uniform boundedness principle. Now, the statement of the Hahn Banach theorem says, if Y is a subspace of a normal linear space X and we have a bounded linear functional defined on Y, that means if F belongs to Y star, then F can be extended to a bounded linear functional F naught on X, and it means the whole space X, F naught, such that norm of F is equal to norm of F naught. Now we already know what do we mean by X star. Now X star, the dual of X is a collection of the vector space or the normal linear space of all the bounded linear maps from X to K, where K is the field of the vector space, and mod of fx is less than or equal to K times norm of X for all X belonging to X for some K positive, which is equivalent to saying that it is linear and continuous. Now what I'm saying that is this statement of Hahn Banach theorem is one of the simplest ones. There are more general versions of there are different versions of Hahn Banach theorem, and most general case would be when we take X to be a topological vector space. But we are not going to go there. We are just going to stick with this version of Hahn Banach theorem and prove it. Now, for the proof of this theorem, and you also must know what I mean when I say F can be extended to F naught. By that we mean now F naught belongs to X star would imply that F naught is a map from X to K, right? That means F naught is also defined for Y, and F naught also sends vectors from Y, which is a subspace of X, to K. When I say F naught is an extension of F, we mean that F naught, when we restrict the domain to Y, it is the same thing. Its action is the same as that of F as a function. So this is the statement. Now it's a very simple statement that if we have a bounded linear functional defined on a subspace, it can be extended without perturbing any of the properties to the whole space X, right? And keeping the norm without changing its norm. So let's start with the proof. Now for the proof of this theorem, we would need a lemma. Now basically the lemma for the proof of the theorem, we first need to prove a lemma. Now the lemma is, if I state the lemma, now again Y is a linear subspace or simply a subspace of X, and X naught is, when I say linear subspace, of course I mean proper subspace. So X naught is a vector that belongs to X but not Y, and it lies outside Y. And if we adjoin, we create a subspace but adjoining this X naught to our subspace X, we will get a bigger subspace, which means that it is basically the span of all the vectors Y union X naught. And we have just minimally extended our subspace to a bigger subspace of X. If that is the case, and again, then given F belonging to our subspace, F being a bounded linear functional on Y, that means F belonging to Y star, we can find, we can extend F, we can extend it to f naught belonging to y star, y naught star, such that norm of f is equal to norm of f naught. Now we want to, in this the case of lemma, want to prove our theorem when we are just minimally extending our subspace to a bigger space. Now of course y is a subspace of y naught, and it's just slightly bigger. It cannot be, just slightly bigger means the minimally bigger space of which it is a subspace. Then the statement of the, we want to prove that, then the statement of the Hahn Banach theorem is true in this case if we just extend it a little bit by just one vector. And then we would use this lemma to prove the theorem in the most general case. Now let us start with the proof of the lemma. Now again, in the case of this lemma, we first prove it under the assumption that X is a real normal linear space. It's a vector space with a vector space that is a vector space over the field of real numbers, not the complex numbers. Then from that we will go to the proof of the lemma when X is a complex normed linear space. That means it's a vector space over the field of complex numbers. So we prove the lemma first under the assumption. I do encourage you to look at the study material, right? Because then the proof is very clearly given there. Of course, this lecture is going to help. Now we assume that first in the case 1 that X is a real normed linear space. That means, of course, जो मैंने अभी कहा कि it is a vector space over the field of real numbers. And of course, without loss of generality, we don't lose anything if we take norm of f to be equal to 1. Because suppose if it is a zero operator, if it is a zero functional, then it's trivial. Of course, zero can be, if zero functional is something that would map everything to zero. Now that can be automatically extended to the zero map itself. So there is nothing to prove. Now in case it is not a zero functional, then I can always take its norm to be 1 without losing anything, because X star is a vector space. Suppose the norm of f was not equal to 1, I take some g norm, a functional g, as f by, it's again a bounded linear map whose norm is 1, and prove the theorem for that without losing anything, and I can just, or it won't affect it. So now without loss of generality, I'm assuming that norm of f is equal to 1. Now let's see our vector space y naught. Now y naught is basically y plus x naught, that is, it is span of y union x naught. Therefore it is basically the direct sum. By that I mean it's direct sum of the vector space, vector subspace y, and the subspace generated by x naught. And what is the subspace generated by x naught? It is all the scalar multiples of x naught. And in this case, since we have assumed that our normal linear space is a real normal linear space, in that case it is just the real multiples, the scalar real multiples of x naught. So that means each vector in y naught is uniquely expressible, and we can express it or write it as y is equal to x plus alpha times x naught, where of course x belongs to y and alpha is some number belonging to the set of real numbers. So every y in y naught can be written like this. Now remember, we already have something that we are given in the theorem. We have a bounded linear functional defined on the subspace y, and we have to extend it to the whole space y naught, which we have actually joined just one vector extra to the subspace y. Now we have to extend it in such a way it is linear, it is continuous, and the norm of f naught is equal to 1, because we have to prove that norm of f is equal to f naught, but we have assumed that norm of f is equal to 1, so we have to show that norm of f naught is also equal to 1. So let's get ahead. Okay, now if we define, let us start with this. If we define f naught from our subspace y naught to the set of real numbers like this, f naught y, which is the same thing as f naught of f naught of x plus alpha times x naught, right? Because every y can be expressed as x plus alpha times x naught, where of course x belongs to our y and alpha is any real number, and x naught is that vector that we have adjoined to the subspace y. Okay, how do we define it? We define it as f of x, okay, plus alpha times f naught of x naught. Okay, now just to clear here, it is basically we are saying that suppose this be a real number, okay, or what I am trying to say is I am going to define f naught of y as f of x plus alpha times r naught, where r naught sort of is a real number such that f naught, this functional, would map that vector which I had adjoined to y to get a bigger space y naught. It would be mapped to this r naught. Okay, now if I define it like this, then I leave it to you. It's very easy to show that f naught is a linear map. It's very easy to show, nothing difficult. You can do it yourself. And if you look at your notes that I have given you, I have written it down, in the notes how it is linear. So, okay, just to keep the video smaller, which can be uploaded easily, I'm not going to show it here. Okay, furthermore, it's also easy to show that f naught, when restricted to y, is equal to f. Again, because f naught of x can be written as, f naught at x can be written as, in case x belongs to y, okay, let me write it, f naught of y, okay, f naught of y, in case y belongs to x, okay, in case y belongs to y, in case, then y can be written as, since it belongs to y, it can be written as x plus 0 into x naught. Okay, then it would be f naught, of course as per our definition, it would be then f of this definition, it would be, because y is equal to x plus 0 into x naught, and by our definition f naught at y is f of x plus alpha into r naught. So therefore in this case it would be f of x plus 0 into r naught, which would be just f of x. But y equal to x plus 0 x naught means that I am saying that f naught at x is equal to f of x. So if y belongs to y, in that case there is no difference between y and x, because I have to multiply here by 0. So therefore I am saying the extension is automatic. That is, the extension is automatic means when f naught is extended to y, restricted to y, then it is the same as f. So it is linear, and extension property also holds. Okay, so now we have to show that it is continuous, and rather it's a bounded linear functional, which is the same thing as continuous, and norm of f naught is also equal to 1. So that's what we are left to prove, and if we are left to prove that f naught is continuous. Yeah, f naught is bounded, continuous, whatever we say, continuous, and norm of f naught is equal to 1. But it suffices, and if both things would be accomplished, if we prove, it suffices to prove that mod of f naught of x plus alpha times x naught is less than or equal to norm of x plus alpha times x naught for all x belonging to y. If we can show that this is true, and of course alpha belonging to the set of real numbers, if we can show that both the things are accomplished, that is, it will prove that f naught is a bounded linear operator on the y naught, because f naught of the argument is less than or equal to some number times, in this case 1, norm of that vector, the argument. So, but if we have to prove that, it is equivalent to proving that, and you know that for any real number, if its mod is less than or equal to another number, so we must have, that means we have to prove that x plus alpha times x naught in norm is less than or equal to f naught of x plus alpha times x naught is less than or equal to norm of x plus alpha times x naught. Okay, now as per our definition, this is f of x plus alpha times some number r naught, some scalar. Okay, so we basically have to prove that this thing is less than or equal to this thing is here the same. Okay, which would imply if we subtract minus fx throughout, we will get minus f of x minus norm of x plus alpha times x naught is less than or equal to alpha times r naught, which is less than or equal to minus f of x plus norm of x plus alpha times x naught, which would be the case if and only if we divide throughout by this alpha and use the fact that f is linear and use the properties of the norm, right? Using the properties of the norm, we can write f of x by alpha minus norm of x by alpha plus x naught, we are dividing by alpha throughout, is less than equal to alpha times, r naught, which is less than equal to minus f of x by alpha plus norm of x by alpha plus x naught. Okay, so if we prove this statement, we're done. Let's call it star, and remember that our x belongs to y and y is a subspace. Y is a subspace, which means it's a vector space itself. Now we observe that for any two vectors, x1, x2 belonging to y, using the linearity of f and of course the properties of real numbers and the norm, we have got f of x2 minus f of x1 is equal to f of x2 minus x1. The f is linear. Now since any real number, now this is a real number because f is a mapping from y, to the set of real numbers, as we are assuming that our space is a real normal linear space. Now every number is less than equal to its mod, so it would be less than equal to f of x2 minus x1, right? And using the fact that this f is a bounded linear map, so this should be less than equal to norm of f into norm of x2 minus x1. But we have also assumed that norm of f is equal to 1. So this should be equal to norm of x2 minus x1. So what we are getting that for any two vectors x1, x2 belonging to y, f of x2 minus f of x1 should be less than or equal to norm of x2 minus x1. So let me write it down here, that f of x2 minus f of x1 is less than or equal to norm of x2 minus x1 for all x1 for any x1, x2 belonging to y. Okay, what does that mean? Then using this, okay, let me see if I can see it in the camera. Okay, I will continue with my argument. Okay, this is what we have shown. So it would imply, I can then write it like this. It would imply that f of x2 minus x1, sorry, f of x2 minus f of x1 is less than or equal to norm of x2 plus this x0, the vector that I had adjoined to y to get a bigger space y0. So x2 plus x0 minus x1 plus x0, which is less than or equal to, of course, using the properties of the norm, I have here added and subtracted the same thing, so that doesn't change anything. So this would be less than or equal to norm of x2 plus x0, using the triangle inequality, of course, x1 plus x0. Okay, which would imply, of course, doing a bit of transposing a number here and there, minus f of x1 minus norm of x1 plus x0. I have brought it here and bringing this there, f of x2 is less than or equal to minus f of x2 plus norm of x2 plus x0. And of course, as I have shown above, this is true for all x1, x2 belonging to y, and y is a subspace. Okay, now what I do, we define two real numbers. Now remember that if I now run x1, now this is true for all x1, x2 belonging to y. So if I run x1 through all the vectors of y and x2 through all the vectors of y, right? This inequality should be still true, right? So now what is this? On the left hand side, I get a real number. On the right hand side, I get a real number. So, but when I run x1 through all the vectors of y, I would get a set of real numbers. Similarly, on the right hand side, when I keep plugging in the values of x2 from the set y, from the vector space y, I would get another set of real numbers. So we define a to be, and of course this set of real numbers on the left is less than or equal to some number, and it is a set of real numbers that is bounded above. So this set of numbers, when I keep plugging in different values for x1, must have a supremum. So I define a to be the supremum of the set minus f of x minus norm of x1 plus x0, x, because I am taking it now to be the general vector x belonging to y, because it could be any vector in y. And similarly, I define b. Now, the set that would be generated by the numbers on the right hand side of this inequality would be bounded below. So therefore, it must have an infimum. So infimum, I define it to be the infimum of this set minus f of x, the set on the right hand side. So x2 plus x0 such that x belongs to y. Now, of course, a is less than or equal to b. That is this inequality. Now what we do, now remember that what we have to prove, we basically have to prove this. If we prove this, then through reverse engineering we will get here, and that is sufficient to prove that f is continuous and norm of f is equal, f0 is continuous and norm of f0 is equal to 1, and that would prove the lemma. Now what I'm trying to say, okay, I think I should stop here. Okay, I would make a second lecture to continue the proof of the Hahn Banach theorem. Okay, let's close it here.